Hello, this is Aaryan Chatterjee, and this is my Lines of Charge Lab 2 in Physics 2212. Before getting directly into the lab, it's important to understand what the lab is precisely covering, which is charge-object interactions. In real life, objects in the world have a fundamental quality called charge, and these objects have a positive or negative charge. However, based on your shape and dimensions, your charge can vary. Now, in this lab, we will focus on analyzing the interactions of two pieces of charge tape. More specifically, the purpose of this lab is to analyze the interactions of two charged pieces of tape and predict the charge of the tape just like Lab 1. However, this time we will model the tape in a line of charges instead of a point particle, which will change the results. Additionally, we will make our computational model to find the charge of the tape with the line charges model. Later, we will see that our analysis and the computational model's analysis will tell us that the charge of the tape was near 2.31 times 10 to the negative 8. But before we jump straight into lab specifics, it is important to understand some of the crucial physics principles and ideas we utilize in this lab. Firstly, it's important that everyone understands Newton's second law, which says that net force equals mass times acceleration, or change of momentum over change of time. Additionally, it's important to know that the force of gravity on an object on Earth is negative mass times acceleration, which is g, or 9.8. Finally, it's important to know that Coulomb's law, which describes the force between two charges, and this is the formula here. These forces will be needed in the observational and computational model to calculate everything, like the charge of the tape using the line charge model. Now we must cover some major assumptions in the experiment, and one is that our object only experiences gravitational and electric force. This means we will not consider any external forces that could have acted on the tape. On top of these assumptions, it is important to know that the system, which is what we will analyze, is simply the top tape, which is tape B, in the experiment, and everything else is the surroundings, like the bottom tape and the ground. To get into some detail about the experiment, we will have two tapes aligned vertically, causing the top tape to float since the tapes repel each other since they have the same charge. Then the top tape will be at rest while floating in the air, and this is due to the electric force and gravitational force acting on the tape. So from Lab 1, we know some important measurements of the tapes which we'll need for the observational and computation model. For instance, it's important to know that the tape's mass is 2 times 10 to the negative 4, the tape's length is 0.2 meters, and the tapes are a distance of 0.024 meters away from each other. But before we get into lab calculations, I think it's important we should review what we did in Lab 1 so we can basically compare our results and the calculations later. Basically, in Lab 1, we found the charge of the tape to be 1.12 times 10 to the negative 8 by setting the force of gravity of the tape equals the electric force on the tape and solving for Q, which can be seen on the slide. So moving on to the lines of charges model calculations, we first have to find the force of gravity on the tape, which is simply the mass of the tape times the gravitational constant, which gives us 1.96 times 10 to the negative 3. Now, since the tape is floating at rest and the electric and gravity forces are the only forces on the tape, we know that the electric force must cancel out the gravity force, meaning the electric force of the tape must be equal to 1.96 times 10 to the negative 3. Since the tape is now a line of charges, we get to model it with the electric force of a rod equation. And since everything is known but the charge, we can simply rearrange the equation and solve for the charge, which gives us the charge of the tape to be 2.318 times 10 to the negative 8 coulombs. Moving on to the computation model, we first put in the known constants like the gravitation, acceleration, the tape's mass, and more. Then we create a function to calculate the electric field from a charged particle to a point. Then in the code, we have a function that creates a line of charges for the tape, which essentially creates a bunch of points on the tapes that have a charge, and the total charge of the tape would be the charge of all the small pieces added up, which follows the superposition principle. Then we have for loops go through every point particle that the tape was split into and find the specific electric force on the top tape. This is done many times for each point particle that is on the tape, which is 30 in my case, and the forces of each point are graphed and added up in order to give us the total electric force of the top tape. Then when the total electric force of the top tape is calculated, we can solve for the charges of the tape, which is 2.18 times 10 to the negative 8, as seen from the code results picture. Additionally, the picture created by the code shows how the tapes interacted with the line of charges model. And from the text below the picture, we can see that the electric force and the gravitational force were close since they need to cancel out, so that the tape can be motionless as float. However, both forces and the calculated charge are a bit different from the observational results, which can be explained by possible sources of errors in the upcoming slides. But before we get into sources of errors, it is important to talk about the results and implications of the models. So from our results, it is clear to see that both the observational and computational model provide similar answers for the charge of the tape with a line charges model, indicating that the tape's charge is around 2.31 times 10 to the negative 8. This indicates that our charges were accurate, but since there is some difference, there are probably some errors. For instance, our calculation could have been wrong since the drag force and other external forces were not considered. We also assumed the tapes to have the same exact charge, but that's not completely true. And we assume that the tapes did not lose any charge from coming into contact with other objects. These sources of error can account for the reason we got slightly different charges for the computational and observational model. Moving on to further conclusions, although we calculated the charge of the tape to be near 2.318 times 10 to the negative 8 for the line charge model, we previously calculated in the Lab 1 that the charge of the tape was 1.12 times 10 to the negative 8 for the point charge model. The model estimates are different because each model represents the tape differently and more or less accurately. For instance, the tape is not actually just a point in real life, indicating that the point charge model simplifies the tape for easier calculations. However, the tape is actually aligned with point charges. So the line charge model is most likely better and accurate. That's all for my presentation. Thank you for listening.